Good morning again, ladies and gentlemen. I will give a second presentation in this session about tunable thermal properties of electrically conducting concrete for energy conversion, storage, and dissipation. And actually, we had a great presentation in previous session from Damian about the supercapacitors, the development of supercapacitors using carbon black nanoparticles. And we showed the potential of the electrically conducted nanocomposite material to store electrical energy. And it is very important because when the discussion comes about the energy consumption and especially the carbon emissions from the energy consumption, we are talking about the critical components. And what better than concrete, than to use the material as a clean energy source. And when we talk about energy, we need to consider two parts of energy, the thermal energy and the electrical energy. So the question here is, can we modify concrete so as to exhibit new functionalities about conversion of these two types of energy, electrical and thermal energy? And this is the topic of this presentation. This presentation is divided into two parts. I will show you nanocomposite materials are able to convert the applied electrical energy into thermal energy. It is also known as electrothermal efficiency. And in the second part, I will present you the opposite. How can a nanocomposite material convert the thermal energy harvested from the surroundings into usable electrical energy? And for these two, we need to study, to examine two critical parameters. For the first case is the electrothermal efficiency that is given from the equation on the right part, on the left part of the slide, and for the thermal to electrical energy conversion efficiency, the thermoelectric efficiency, we talk about the thermoelectric figure of merit. And if we will take a close look at these two equations, we will see that there are specific properties that governs, that dictates this conversion efficiency. The electrical conductivity, sigma, thermal conductivity, lambda, and specific heat capacity, Cp. In both cases, we see that we need increased thermal conductivity. However, when the discussion comes to the thermal conductivity, we see a change. For an electrical to thermal energy conversion efficiency, we need to increase the thermal conductivity, while for the thermal to electrical energy conversion efficiency, we need to decrease the thermal conductivity. So, for this presentation, we prepared 28-day cementitious mortars reinforced with nanomaterials with different intrinsic conductivity, such as carbon nanotubes with high electrical and thermal conductivity, and nanocellulose carbon fibers, which are insulators with very low electrical and thermal conductivity. So we dispersed the materials following a specific patent by Professor Shah and Professor Consta to prepare, again, mortars reinforced with nanotubes at amounts of 0.05% up to 0.2% per weight of cement, and nanocellulose fibers from 0.1 to 0.5% per weight of cement. And to calculate actually the electrothermal efficiency and the thermoelectric figure of merit, we conducted electrical conductivity measurements to measure the electrical conductivity, thermal conductivity and specific heat capacity, and the thermoelectric power, the Seebeck coefficient for the thermoelectric figure of merit that I will talk in the second part of this presentation. So here we see the results that I present in a previous session about the electrical conductivity, and to sum up, we see that the electrical conductivity of mortars reinforced with the carbon nanotubes. And to sum up here, we see that by increasing the nanotube content up to 0.1, we increase the electrical conductivity up to 2.5 Siemens per meter. And after this amount, the electrical conductivity values reach a plateau. Essentially, what I'm showing here is the percolation threshold that is around 0.1% per weight of cement for this type of carbon nanotubes. In a similar way to the electrical conductivity values, we have two other properties that essentially dictate the electrical to thermal energy conversion efficiency of the nanocomposite material. And we talk about the thermal conductivity and the specific heat capacity. And I will start with the thermal conductivity, lambda values. Here I'm showing the results of the mortars reinforced with the nanotubes starting from low amounts up to 0.1, and then for higher amounts up to 0.3% per weight of cement. And we see a different pattern here comparing to the electrical conductivity. We see that the thermal conductivity values increases up to 0.1% per weight of cement nanotubes from 0.82. The neat mortar without the nanotubes is an insulator, so exhibits very low thermal conductivity values. And this value increases up to 1.44 with the addition just of 0.1% per weight of cement. Above this amount, over this amount, by increasing actually the conducting nanomaterial, we see decreases, slight decreases of thermal conductivity. And actually, the conductivity proportionally decreases by increasing the carbon nanotube content. And this is something that we need to go deeper and explain. Before I continue, I just want to show you the scanning electron microscope pictures here for the amount of 0.1. We observed individual nanotubes. We are able to measure also the diameter of these nanotubes. And essentially, we are talking for monodispersed nanomaterials, while for 0.15% per weight of cement of nanotubes, the ultrasonication process that we applied was not that effective. And we see small agglomerates stacked on the bottle of the walls of this bottle, and also agglomerates from the scanning electron microscope. So, if I continue here, we see a relationship between the thermal conductivity and the specific heat capacity. Indeed, by increasing the amount of nanotubes at 0.1, there is a decrease in thermal conductivity and the corresponding increase in a specific heat capacity. Actually, there is a thermal diffusivity, increase of thermal diffusivity in the nanocomposite. For higher amounts, as I mentioned, thermal conductivity is lower, and see the high increases of the specific heat capacity. That means that the nanocomposite with higher amounts of nanotubes is able to store energy here. So it's able to store both electrical and thermal energy and increase its heat capacity. As a result, the thermal conductivity slightly decreases. And as I mentioned before, for amounts higher than 0.1, we see agglomerates due to the incomplete dispersion. So, in other words, a uniform dispersion of the carbon nanotubes plays a key role on mitigating the specific heat capacity values. So we can increase the thermal conductivity. And this relies in the so-called interfacial thermal resistance. So what we saw is that the agglomerated nanomaterials potentially contribute to the resistance to thermal flow, which is, again, also known as an interfacial thermal resistance. As a result, the specific heat capacity for amounts higher than percolation increases, and the thermal diffusivity of the material of the nanocomposite decreases. So, it is apparent that dispersed carbon nanotubes contribute to the nanocomposite's ability to convert and apply the electrical energy, because we apply electrical energy to measure all these values, to thermal energy. And from the equation here, we can summarize all this research using this equation, the electrothermal efficiency, that we can calculate using the electrical conductivity, thermal conductivity, and specific heat capacity values. Here is the calculation for plain mortar, no surprise, 15%, very low electrothermal efficiency. It is, we talk about an insulator, and see the dramatic increase by using nanotubes at an amount of 0.1% per weight of cement. We are talking for just a calculation, but from the calculation we see 99.5%. So that means that the material, the nanocomposite, is able to almost completely convert the applied electrical energy to thermal energy. And this is particularly useful for applications such as de-icing or anti-icing, because by applying just a low amount of electrical energy, and we talk about an electrical current of 2 volts here. We want to avoid thermal shock of the nanocomposite. We see a complete conversion of this current to thermal energy. However, for amounts higher than 0.1 of CNTs, we see decreases of the electrothermal efficiency. For 0.2 CNT reinforced mortars, almost 95%, and even lower for 0.3 CNT reinforced mortars. That means that the material exhibits a lower conversion ability of the applied electrical energy to thermal. And I will continue with the second part of this presentation. I mentioned that in the beginning that we also examined the thermoelectric figure of merit, the ability of the material to convert thermal energy to usable electrical energy. And for this, we need to examine the electrical conductivity, thermal conductivity, and the Seebeck coefficient, which is the thermoelectric power generation ability of the material. And because this study is a little complex, is a little confusing, we set some benchmarks here. The benchmarks here are some values that are required for generation of electric current of a voltage of at least 1 volt. All right, so we prepared some elements here. And from empirical investigation, experimental and equations, we set these benchmarks. We need an electrical conductivity higher than 1.9 Siemens per meter, thermal conductivity lower than 1 watt per Kelvin meter, and a Seebeck coefficient higher than 1300 millivolt per Kelvin. So we can reach a thermoelectric figure of merit at least 10% that is required to generate 1 volt. The results here shows the electrical conductivity, thermal conductivity of the CNT reinforced mortar are 0.1 only. We see indeed that we reach the value that is needed for electrical conductivity. However, the material exhibits high thermal conductivity. For sure, we use a highly conductive nanomaterial here. So we need to increase this component, this part, thermal conductivity. And for this, we introduce a material that exhibits insulating behavior. Low electrical and thermal conductivity. So we introduced in the 0.1 CNT mortar nanocellulose fibers at amounts from 0.1, 0.3, 0.4, and 0.5. And here are the results of the electrical conductivity. We see that by adding nanocellulose fibers, indeed we increase the electrical conductivity, but no lower than 2 Siemens per meter, because the percolation threshold is here, the continuous network is already established, and the nanocellulose fibers do not reduce the conductivity, electrical conductivity of the material at a large extent. Here, in the right part of the slide, are the thermal conductivity results of this hybrid mortar nanocomposites, and we see that the addition of nanocellulose fibers 0.4 and 0.5 reduces the thermal conductivity of the material lower than 1 watt per meter Kelvin, 0.9 and 0.8. So this combination shows us that we can keep a high electrical conductivity above the benchmark while effectively reducing the thermal conductivity, which is desperately needed for the thermoelectric effect by this combination. So keeping these two samples, mortars with CNTs 0.1 and nanocellulose fibers 0.5 and CNTs 0.1 and nanocellulose fibers 0.4, we prepared a custom-made experimental setup to measure the thermoelectric, the Seebeck coefficient. Here, the Seebeck coefficient, which is the thermoelectric power generation ability of the material. And we calculated and measured, actually, that the Seebeck coefficient for this particular sample is around 1900, higher than the minimum threshold that we set previously for the generation of current of 1 volt. To summarize, here is the thermoelectric figure of merit of this particular sample with CNTs 0.1 and nanocellulose fibers 0.5, and we reached a thermoelectric figure of merit of 16%, which is sufficient for generating electric current at a voltage of 1 volt. So, to showcase this concept, we prepared actually a laboratory demonstration in our lab at UTA, and I will show you this thermoelectric concrete battery for renewable electricity generation. We used 2 components. We applied a heat source using a halogen lamp. We measured the change on the temperature and the voltage. And we also connected the 2 concrete components with an LED lamp to see if we can lit it up. In the next, I will show you the video of this demonstration. Here we see the 2 components that there is a halogen lamp over here giving thermal energy. The 2 components are connected with an LED lamp and also with a voltmeter. We see that by supplying thermal energy, we increase the thermoelectric, the Seebeck coefficient, the thermoelectric figure of merit, and in 10 minutes we illuminated this light bulb. Of course, the intensity of this light bulb, of the light, is very low, but after 18 minutes we see from the light bulb, of course, and the voltmeter that we generated 5.5 volts. There is a full illumination of light bulb. And the third, very important conclusion from here is that the LED lamp was lit up for 18 minutes. That means that the material, the nanocomposite, was able to provide this electrical energy that was generated for 18 minutes. So this opens up the concept for a thermoelectric concrete battery material that can store for long term and distribute this electrical energy. So to conclude, in this presentation, I presented two parts. One part for a nanocomposite concrete for electrical to thermal energy conversion efficiency. We showed that by adding nanotubes, dispersed nanotubes of 0.1% per weight of cement, we increase the thermoelectric, the electrothermal efficiency. This is not correct. It was 15% up to 100. And also for the second part, the thermal to electrical energy conversion efficiency using a combination of CNTs 0.1 and nanocellulose fibers of 0.5%. We generated voltage of 5.5 volt. I would like to acknowledge here our NSF project with Professor Sobolev and Professor Beleng. Thank you so much, and thank you for your attention.